Good morning, everyone. My name is Alex. Today we're going to talk about code design in Raft on a thread per core model. For the Kafka API, all of the code will be available on GitHub today. This is for QCon. So background, my name is Alex. Feel free to find me on Twitter if it's probably the easiest way to engage with me. But I'm a developer. I originally wrote the storage engine and all of the techniques that we're going to cover today. I was heavily involved with either as the developer that wrote the code or as a reviewer on the code. We've been hacking on on Red Panda, which is the project that we're going to talk about today. It's a streaming platform for mission critical systems. Prior to this, I was an engineer at Apache through an acquisition of Concord.io. You can think of it like Spark streaming, but we wrote it in C++ on top of Mesos. The agenda today will cover two observations, a new way of building software using a thread per core model, and the practical implementation. Specific will cover 8 techniques for building low latency software. And so the first real observation here is how hardware is fundamentally different than it was a decade ago. The second observation is that given the fundamental shifts in hardware, CPU becomes the new bottleneck for a storage system like ours. And so embracing the hardware where everything is asynchronous is really the second observation. And so with these two premises, we can reason about how to build new software, or what are new techniques to build in software. In particular, we will walk through the 8 most impactful techniques for Red Panda to achieve 10 to 100x better tail latencies. I'll highlight that all of the source code that I'll be talking about today is available on GitHub. So if you have any questions, if you want to interact with the code or the software, feel free to go on GitHub and ask us questions, etc. One of our advisors really loves this saying, and it goes, sometimes you get to reinvent the wheel when the road changes. And the road is the hardware in this analogy. The idea here is that hardware is fundamentally different from what it was a decade ago, in particular for storage engine. And in the things that is materially different is, one, disks are 1,000 times faster, and at the same time, they are 100x cheaper. The second material improvement on hardware over the last decade is that computers are 20 times taller. So you can go on GCP and run a 225 core vCPU VM, and so massively different scales, and the contention moves for a storage engine out of the spinning disk subsystem for older storage systems to CPU coordination. And then the last one that I think is worth noting, and I didn't highlight it here in bold, but it is an important distinction, is that in the LAN, basically on Amazon, you can go and rent 100 gigabit per second NICs and actually get that sustained traffic delivered to all of the VMs. And so the idea is that software doesn't run on category theory. It runs on the superscalar CPUs with massive amounts of memory, multi-socket motherboards, disks that are actually 3 orders of magnitude faster. And so you start to move the bottleneck in compute to a different subsystem. This is an evolution of the system that I'll talk to you guys about today. In particular, the mental modeling techniques and how it evolved through history superimposed with the evolutions of hardware. And so RabbitMQ really came about and replaced a bunch of older enterprise, kind of old school message queuing like TIBCO and Solus. And around that time, SSDs were about $2,500 per terabyte. In 2010, 2011, Kafka came out, really bringing a lot of the MapReduce style thinking to streaming. The idea is, can you do streaming on cheap spinning disk type computers with 4 vCPUs, perhaps maybe a gigabit of network, and the point I want to highlight here is that the threading model and the mental model for building software a decade ago was for a totally different bottleneck in computing, namely that to write a page to spinning disk, it was in the order of milliseconds rather than microseconds. Pulsar came about as the evolution of streaming here and added the disaggregation of compute and store, largely with the context of HDFS. In the public clouds, the S3 API became the true disaggregation of compute and store. And so as of this year, Red Panda is now stable and ready for production use. And what I wanted to highlight here is that it's software designed for the modern platform. And so when we ask ourselves, what could we do differently if we were to start from zero? We knew where we wanted to be, which was to provide, effectively a Raft implementation on with the Kafka-API, given the modern platform, given the modern hardware. The second observation here is that everything in hardware is actually asynchronous. The most important point of this slide is really that even on an NVMe SSD device, the one on the right is Western Digital NVMe SSD device, you can have sustained writes throughput of 1.2 gigabytes per second. However, if you use the classical model of I/O, where it's blocking, right? So you do file write and you give it the file handle and some bytes, and then you do file close, right? So basically synchronous and sequential in your program. To write a single page to disk, you're roughly wasting 60 to 420 million clock cycles. And so the observation here is, could the CPU be actually doing something else instead of waiting for the hardware to complete the operation? And obviously the answer is yes. But from a software construction perspective, is if we embrace the platform, if we embrace that hardware is always asynchronous, and we design our software from the ground up to be asynchronous first, then we get to take advantage of this 420 million clock cycles that are wasted to do other interesting work like compression or verifying, checksum and verifying the integrity of your data, or pulling more data out of the network while your NVMe SSD device is busy writing it to the actual sectors of the NVMe controller. The architecture that we chose to build Red Panda on is on a thread per core architecture. And for building a storage engine, we think that we've measured, right, that the new bottleneck is CPU. And so how do we start to build on a new way to build new storage engine or new software using a thread per core architecture? The distinction here is that asynchronicity is a first-class citizen, and it becomes explicitly how you start to reason about your software building. A word of warning, though, is there's no real free lunch here. And when you move to a thread per core architecture, you will end up rewriting large parts of your software that come with built-in threading models. A classical example is that often you add a logging library to your program, and it has this thread pooling implementation. Well, that doesn't really work that well with a thread per core architecture, where every logical core presented to the program is an actual p-thread, and inside that particular p-thread there is a cooperative scheduling implementation. And it doesn't necessarily have to be the way that I'm going to explain, but this is rather an example of an architectural thinking that you can leverage. So the idea that we're going to cover is in C++, because we wrote the storage engine in C++, in large because we're trying to extract every ounce of performance of the hardware. And so it was important to us to be able to access all of the lowest level primitives. So this cooperative scheduling framework with C++ features, and we use a library called C-star that gives us this thread per core architecture and a cooperative scheduling mechanism. And so Go has a similar thing where every time you return on a function call, the cooperative scheduler gets to choose what is the next Go routine that is going to run. Similarly, for C star, every time you return a future, the future is either executing or suspended. There is no other state about this particular future. And so what it is that you start to worry about software, about the concurrent structure of your program rather than the parallelism. And the parallelism is a free variable that is decided at runtime. So you can take a program that was built for concurrent structure on your 4-core laptop and run it on 225 physical cores, or say virtual cores, presented to your program on Google, on GCP, and know that because you've programmed to the correct concurrent structure, parallelism is a variable that you can tune at runtime. The idea here is that these futures are viral primitives. And so just like actors and, in frameworks like Orleans or Akka or Pony, the language, they're really composable. And so you can mix them, map reduce them for an aggregation. You can filter them, chain them, complete a particular future. You can have a generator. Sleeps, for example, is a really powerful mechanism because sleep on a future is actually just a suspension of the particular frame. In C star, the framework that we're using, it gives you no locks. Once you enter the thread local domain, you don't have to worry about other actual parallel access to the same variable, because there's exactly one thread to do everything. And so it's really freeing. It is limited in that there's exactly one unit, one way to write code, but it is freeing in that as long as your domain fits into this thread per core model, and we made the Kafka-API fit in this model, so we think it's fairly flexible, then you no longer have to worry about parallel access to a particular variable. And so a lot of problems with parallel programming just sort of go away, because you are sort of explicitly doing this from the get-go. So we'll cover 8 techniques in this talk. The first technique that we used to achieve 10 to 100x lower tail latency in Redpanda and exposing the Kafka API was to use no virtual memory. And this is rather a contentious subject. But what we do is remember that we're using a thread per core architecture. And so when the program starts up, we allocate the entire machine's memory, and we actually do some reservation for the operating system and daemons, etc. But the point is that you take the memory that you present to the program, and the program allocates 100% of the memory presented. And then you split the memory evenly across the number of cores. So let's say that you have 10 cores and 20 gigabytes of RAM. Well, then every core is going to have 2 gigabytes of memory for it. And that is it, 100%. Like, as in, if your core allocates more than 2 gigabytes of memory, you will and crash your program. But what it gives you is this low latency thread local memory allocation access. And at the lowest level, we use a buddy allocator. And a buddy allocator says it's this basically, it divides memory by half every time it needs a new region. And so the mental model is that for allocation pools, right, every time you say new integer, it has to come from somewhere, right? And so we swap the allocator library so that all allocation pools below 64 kilobytes are, part of a range of allocations, so that you could recycle the allocations, etc. And everything above 64 kilobytes just gets added to the large memory pool allocation. And so one thing to highlight here is this: it is difficult to use this technique in practice, because every data structure, you have to think a priori. You're like, oh, how much memory am I going to dedicate to my RPC subsystem versus my compaction and my background threading model versus any other part of the subsystem, or my read ahead for the disk, or my write behind. my training for my dictionary compression, etc. As a programmer, just like you have explicitly opted into a concurrent and parallel execution model, you're also opting in to deciding explicitly where and how your memory is allocated. And this is perhaps one of the more difficult mental sort of modeling techniques that we have to retrain, that we had to retrain ourselves, so that we don't especially this is really hard as memory fragmentation increases over time. The second technique is we call iobuf, and it's a thread per core buffer management system. So the idea with thread per core architecture is that once you land on a particular core, and let's reduce the mental complexity model for the sake of this talk into having a single core, right? Let's say 2 cores, so that the mental model is simple. For fragmentation, as your program runs over time, let's say weeks or months, your memory is going to start to look like grated cheese, right? Like it has this particular holes of memory. And so what an iobuf optimization does for us is that instead of forcing a reallocation and compaction of memory, where it's similar to the disk defragmentation in the Windows, on the spinning disk days, where you would click, defragment disk, and it would take a bunch of fragments and put them together, and all of a sudden your program would get faster. So similar things happen to memory, where as a function of time, your program is going to allocate memory in the entire memory region allocated to it, and it's never going to be pretty. It's never going to be like the program always allocates from the bottom part of the memory. It's just the allocator just keeps a pointer to where it is, the next free slot, and then it moves around and scans until it finds the next pointer. And so it's a really low latency in that it doesn't do any compaction at runtime. This is fundamentally different how some of the virtual memory subsystems work, but fundamentally we never allocate a large linearized memory, because that puts a lot of pressure on our memory allocator, the body allocator. And if not done correctly, if you do that for really large allocations, then you can actually end up ooming your system. Remember that we only have usually around 2 gigabytes per core, and we don't use virtual memory. And so what this is saying is like, let's embrace that you are going to be mostly in a memory fragmented world, and let's just use memory as efficiently as possible without causing this latency spike of causing a compaction, where you take all of your memory, you recompact it to the bottom part of the region, and you leave the upper regions of memory free, so that you could do linearized memory allocation. Instead, we built this structure that allows us to iterate over data structures as though they were contiguous memory in code, but in reality is backed by a bunch of fragmented buffers. We weren't the first ones to invent this thing. The Linux kernel has a kbuf implementation that is very similar, and the FreeBSD kernel has another implementation called embed, which is exactly the same. And these techniques have been around for a long time. What we've added here is we've sort of tied it to our thread per core architecture. And so instead of having a global deallocation pool, when you send memory to a remote region, instead of calling free on that remote region, because that region doesn't own, that particular core doesn't actually own the data, it'll send a message back to the originating core, and then the originating core has to delete the memory. And this is sort of all handled for you as a buffer abstraction. And so as long as you build everything on top of this buffer abstraction, largely your code ends up looking roughly similar or the same. The next technique is out of order writes. And this is really important for trying to maximize throughput of the device. As in, like, your physical hard drive has a particular set of parallelism and also concurrent structure. But to highlight this technique is we ask the file system, hey, give me your alignment for writing a page to effectively the NVMe SSD controller, and it tells you, let's say 4096 bytes is the alignment. And so when you allocate something, you say, okay, give me a hardware align 4096 byte boundary, and then I'm going to write the page. In this particular case, the size is 128 kilobytes for this example. And instead of dispatching one, waiting for acknowledgement, dispatching the next one, waiting for acknowledgement, and so on, we dispatch them all and simply do this scatter gather approach to writing a particular set of pages, so that what we are doing is we're trying to saturate the hardware while minimizing latency. So you're doing both things here. You are reducing the latency for a particular batch of operations, not a particular operation, but a particular batch of operations. And so the average latency is much lower, right? So the average latency for writing a block in this case is higher, but the average latency for writing all of them is much, much lower. It's probably like 1.5x the cost of writing one. And your throughput in this case, could potentially quadruple. So this is a really powerful technique when you're trying to saturate the DMA device, the NVMe device. The next techniques that we use, sort of building on top of this thread per core architecture, is no page cache. And this is, the second most controversial thing for us. For the particular application that we're building, which is a Red Panda, a drop-in Kafka replacement, right? So we give the user a Kafka-API. You can take your 100,000, Kafka-API compatible code and point it at Red Panda, and it should just work. There should be no code changes. So that's the API we give the user. Kafka as an API has a very specific, it is a very specific problem. It is not a generic problem. And so to us, the Linux kernel page cache actually introduces non-determinism in the I/O path. And at worst, it introduces correctness bugs. So let's walk through it. Every time you instantiate a file handle, the kernel will instantiate a page cache object that has global lock-in semantics for that particular page cache object. So if you have two writers, or if you have a writer and a reader, they're all competing and contending on that particular lock. Especially if you have tailing iterators, to get exclusive access to that particular memory region. So that's the first one. But we've architected our code in a way that is a thread per core, which means we have a single thing at any point in time accessing files. And so perhaps the way I like to frame this as a general rule of thumb is that the page cache, the generic page cache, is never a bad choice. It's just always not a good choice if you have an application-specific problem that you're trying to solve, like offering our users, effectively a log interface with the Kafka-API access patterns. And so it is always really a good middle ground to use, and writing your code against DMA is really tricky and hard to get right. And it took us a couple of years to make sure that it's solid and it crashes correctly and so on. And the last one that I'll mention here is that it introduces hard to track bugs. And I linked in the presentation a Postgres bug where it was basically the bug was there for 20 years in Postgres, and Postgres is one of the better engineers out in the world. And so you can start to understand why a generic scheduling algorithm is not really that useful when you have specific embedded domain knowledge about the problem you're trying to solve. What eliminating the page cache gives us, though, in particular for performance, because remember the goal is to get 10 to 100x better tail latencies, is that it gives us a thread local, so really low latency cache, that the format is ready to be shipped straight onto the wire. So there's very little translation, right? We move away from caching pages into caching objects. The reason that works for us is because the Kafka model is just a header with a bunch of payload data. And so we pay the cost of materializing the header a priori so that we can just take that entire byte array and ship it over onto the wire when the next request comes in. So there's really no translation. And perhaps more fundamentally is that we can learn the statistics from the file system latency backpressure and actually fail the next request. One example is, assume that you're trying to heartbeat a particular endpoint, and you know that in order to do the next heartbeat, you have to write some data on the file system. Well, we know if the current latency is twice as much as the next heartbeat, then we can simply fail it without adding additional throughput or latency onto, that is effectively wasted work on the disk. And so that transparency really busts a lot of performance when you get to the saturation, when you get to the tail latency scale. So above 99.9 percentile and every percentile between that and the max latency. Another big allocation, and we have 3 left, is adaptive allocation. This is really a trivial thing that I think a lot of applications could really benefit from. You don't really need even a thread per core architecture here. The idea is that every time you update a global metadata, like your file size, it incurs all sorts of additional costs in the Linux kernel. It might have to update other inodes or other metadata, whether it's folder metadata or just the file system metadata. But anyways, that operation is a global operation and it requires a lock on the kernel. And so what we're doing here is you can use the fallocation syscall to effectively write zeros every 32 megabytes. And so instead of doing fsync, we do fdatasync because we know we have the size. And every time we're about to hit over that 32 megabytes, we pre-allocate another 32 megabytes. And in real life use case, that has anywhere from 15 to 20% latency improvement by doing this ahead of time. Effectively what you're doing is you're amortizing the cost of updating metadata in the kernel. How does all of this relate to Raft? By bypassing the page cache and the virtual memory and all of these techniques, we get to embed hardware level knowledge into Raft. But one really interesting use case that we found while trying to reduce the flushes, which are a global file system operation, is every time you write in Raft, you have to flush to guarantee durability of the writes on disk. And so what we did is we learned from the guys that were building hardware where they get to scan the next series of operations and reorder them as long as the resulting set doesn't change the semantics. So we can't change the write order, but what we can do is we can drop the flushes. If you have a write flush, write flush, write flush ratio, what we do is we say, okay, for this batch of operations, we're going to write 3 times, drop 2 flushes, and then flush at the end of the call. And that has this huge performance improvement at the cost of a throughput improvement, at the cost of actually artificially debouncing latency. So actually increasing the latency just a little bit reduces the overall system latency and increases the throughput. And so this is really useful for us, and we do this because we get to learn transparently what the latencies being propagated from disk are all the way into higher application level protocols. And so this gives, if you really think about it, what we're doing here is we're just doing better buffer packing at the lowest level bits, right? And instead of writing half a page flush, read the next half page, etc., what we're doing is we're writing bigger buffers and then we're flushing bigger buffers and we're reducing the number of flush operations. Then the next one that I think is really important when you build the thread per core model is an execution model for pipelining. And pipelining is really critical in order to get latency. Why? Without pipelining, you can't do the debouncing trick that I mentioned, right? So if you dispatch one request, wait for it to finish, and then do the next one and do the next one, that sequential ordering is really, really slow. And so what we do is the dispatching. Once you get a TCP connection accepted, let's say in this example is on core 0, and you write into both core 0 and core 1 in this particular example, what we do is we figure out the assignment of, okay, which cores are actually going to handle this particular data. And then for those cores, we simply pipeline the writes. So if they're on 2 different cores, you're actually getting true parallelism. And if you're in the same core, then you're getting pipelining, and you can take advantage of a lot of other optimizations like the debouncing for lowering the number of flush operations. And the last one, perhaps the most important one that you'll do is when you adopt a thread per core execution model, its metadata becomes really difficult. And the idea is that you no longer have global metadata. And so if you don't have a global metadata, you always are going to be operating on a stale metadata. And so you have to embrace that idea, right? You will never have a global view of the data. It is very expensive to do a synchronization event across 225 cores, right? That includes basically pushing a barrier to all of the cores, serializing the metadata, and then making sure that every core has a copy of it. Instead, what we do is every time we send data to a remote core, we piggyback information on the way back that is useful to the protocol dispatcher. So for the Kafka model, we say, okay, go write this partition on a remote core, and on your way back, tell me what are the latency statistics of disk for that particular core, how much data is there on that particular core. If this TCP connection is a consumer, let me know what is the gap between my head and the tail of the log so that I can start to do an execution planning on the next phase that comes in. And this particular metadata piggybacking has had some of the most profound effects in simplifying the architecture. So we could do this many different ways. You could add an exception to the rule and simply say, okay, for metadata, we're going to have a global lock, etc. But what we found is that piggybacking information is very cheap, computationally speaking, right? You're copying integers around. And two, really gives the TCP connection the view that it needs to do the job. It doesn't have to be correct at all times. And by correct, it just can't be incorrect, right? It can have a partial view of the data, which is fine because not every core needs to have an understanding of what every other core is doing. It just needs to know the information that it needs to know. And so it's a much smaller problem, and piggybacking information on the way back from a remote core to the originating core was one of the most profound architectural differences. With that, I will wrap it up. The bottom two graphs show what are the difference in impact in terms of performance. And what I'll highlight here is that a lot of these techniques are really aimed for anything above the P90th percentile. As you can see, I'm comparing Kafka in black with Red Panda in red. And once Red Panda understands the hardware saturation, right? If your hardware isn't being saturated, there's really very little that we could do if there's lots of room for computation and growth, and there's really no back pressure. All of these techniques matter when you start to care about the tail latency, when you start to care about, basically the entire distribution of your users, and when you care to give predictable performance to your application. All of this code is available online. If you have any questions, I'm always on Slack. Feel free to chat me there, or feel free to say hi on Twitter. Hope you enjoy. All right, thanks.
Excellent talk. We have only about 5 minutes for questions. I think, can you join the Hangout just after this?
Sure.
It's on Zoom, so if people have questions, that's the best way to talk to you. I think you've answered a bunch of questions already. I think listening to this, one question I have is, do you still need an operating system, or has the operating system become your enemy?
Yeah, that's a great question. I've thought a lot about this. Not as much as other programs do. We really kind of want to own most of it for predictable latencies, and so the next step for us would be to write our own file system, and we're actually not very far from it. So if you look at the Kafka-API, we keep track of timestamps, of offset, of metadata. We have multiple indexes. And so, I've thought about actually writing our own file system so that it just, like, you open up a block device file as opposed to open up a file handle file. You just open up just the device block file and you do a little bit of recovery. And we have to do a lot of these techniques already if you're any kind of storage system, because if the system crashes, you have to look up some metadata and then you have to recover and recheck some that the data is the thing that that the program said it is stored. And so if we have recovery, if we have timestamp, if we have offset, we have sizes, we have metadata compression, then what is the file system really doing for us? What it's really doing is sort of being compatible with other programs. And the reason we haven't gone into just a full-on include OS is that there's just other programs that people need to run often on the same machine, whether it's for authorization, authentication. Like in our cloud, there's like an SSH program that verifies that only the SRE is allowed to SSH into that machine, and so it becomes kind of an operational hassle to just own the really create your own OS image. But yeah, right now, you're right. I think that's a really fantastic observation. We really try to just own the whole thing, which is it's funny.
Yeah, it seems, I forget the name now, but there's a trend of doing sort of exokernel type development, where you basically link your program into the kernel. As long as you use a safe language, it's fine. So if you consider that maybe as an option, or rump kernels, I think they're also called.
Yeah, no, and there isn't that much, like all we need is really the initialization sequence of like, okay, bootstrap and really start this process. But in terms of owning it, in terms of like managing memory, like you mentioned, CPU, cross-core, one of, I think the hardest thing was to do proper CPU accounting. And I posted a link on the chat. It's really not just crossing the memory boundary, is actually crossing the memory boundary with accounting. So you say, okay, what is my budget to live my core, and otherwise I need to do local operations before I spend all my budget, all my latency going to remote cores. And so once we got that worked out in Red Panda, then the rest, I really started thinking about that. There's so many cool problems to solve that it's hard to work on that.
Right,
I think
right.
Linux, yeah. So
we have 2 minutes. Maybe this is a bad question to ask with 2 minutes to go, but what do you think about has the rise of ARM on the server? Is this interesting for you, or is it
hugely interesting? Yeah. So we're releasing ARM support hopefully this week or next week, ARM VA support. And what it does is actually your price per byte on a storage subsystem, even for your active workload, is hugely cheaper. It's like 30%, 20 to 30% cheaper on the price per byte or price per dollar per cycle basically spent. It's very, very cheap. I know. I think it just has to do with the cost of how Amazon is renting those computers to you. It's just cheaper. But yeah, and what's an interesting stuff? It's someone in the audience asked it, which is this designed for super high, like super tall machines? And the answer is actually the opposite. And the idea is that when you design your system concurrently, then parallelism becomes a free variable. So we have this embedded firewall company that is using us in an ARM setting, actually not an ARM setting, just in a single core in a distributed router. And instead of using the file system, they use the Kafka-API because they get ACLs and TLS and a bunch of like security and user management, and so encryption. And so yeah. Anyways, I think that is a really interesting thing to think about, parallelism and concurrency, where parallelism is just the number of cores and it's this free runtime variable, and so you can run from 1 core all the way up to 225 cores.
Right. So I get the signal that we have to wrap up, but I think we'll see you in the Hangout room. Thank you, Alex.
Yeah. All right. Thank you, guys. Bye, everyone.